So this is one way to look at the overall process of the isoparametric element formulating the stiffness matrix. So I've done this in Mathematica with a 4-node quadrilateral element, and so I think if I go through this slowly, you can see how this works, and I'll post this word notebook or whatever Mathematica calls it online, so you can tinker around with it. So if you imagine, the first thing to define an element is actually the nodal coordinates. So first off, what we've done here is define the nodal coordinates, the x and y nodal coordinates. Oops. Just get them lined up. I don't know why it's not lined up. Oh, that's weird. Okay, whatever. So this is what I want to kick though. Okay, so you can fool around with these however you wish. So we evaluate that. The next, so obviously x and y are the coordinates, node 1, node 2, node 3, and node 4. This line here just plots the shape of the element. So in fact, you change the second node and maybe move it off the line a little bit. Point to 2. And you can see if we change the plot, the element plot changes. So you could tinker around with the element itself. The next line is we just define the shape functions with respect to the parent space psi and eta. Now again, this in most finite element codes, this will be hard coded in. So this is the same, regardless of what are the nodal coordinates. And in this section here, we just plot those out. That's for the first shape function. You can see it goes to 1 at node 1. This is being plotted in the psi eta space. You can see, so it goes from -1 to 1. So this is the psi direction, and this is the eta direction. So here's the shape function for the first node, and then here they are for all of them. First one is here, second one is here, third one's here, the fourth one's here. You can see they all have the same type of shape. They look like a plane, but they're twisted a little bit because a plane can't quite go to 0 on the two perpendicular lines of psi and eta. So that's the bilinear term that gives that little twist. All right. So next we can get the mapping, x and y as a function of psi and eta. So that's what these two lines here are. So remember, we're just using the interpolation. So it's the first shape function times the x coordinate for the first node, second shape function times the x coordinate for the second node, so on and so forth. So it's the same interpolation as you would have for u or v or anything else. And same for y. And for these particular elements, this is what it turns out to be. Now, if you change the nodal coordinates, this will obviously change. We can also get the Jacobian matrix. And here you can see the Jacobian matrix is a function of position. It's a function of psi and eta. So depending upon where you are in the element, you'll get different values of psi and eta. And you can also analytically get the determinant of the Jacobian. All right. And from looking at this, you can see that really there's nowhere in this element can the Jacobian go negative, because even if you set eta to 1 to make this as negative as possible, and psi to -1 to make this as negative as possible, it still is only minus 0.25 off of 0.75, so that's going to be problematic. Now you can see if we go back, and let's really distort the element. Let's push this node down through the midpoint. So that's node 4. Let's put it at, how does that look? Yeah, if we do it even less, if we do it to this degree, we definitely should get a negative Jacobian. Okay, so you can see we've actually push the fourth node beyond the line connecting nodes, 3 to 1, right? So that's definitely going to give you a negative Jacobian. Shape functions are still the same. We can redefine the mapping. That's changed. Now, this is the Jacobian matrix, and now here becomes the determinant of the Jacobian, and you can see if we put in eta equal to 1 and psi equal to -1, this gives me a value of -0.45, which will make the Jacobian negative. So that's around in the region of eta equal to 1, psi equal to -1. So that's the region, if you think about it. Eta equal to -1, I'm sorry, psi equal to -1, eta equal to 1 is up around this node 3, and that makes sense because that is the one that we pushed through. So you can see that gives me a problem. That would give you the negative Jacobian. But there's still regions where the Jacobian is positive, right? If you look at 0, 0, it's positive, right? So it's not negative everywhere, but that's where you would start to have some issues. So let's move this back and make this a little more normal. Okay, that looks more like a reasonable element. Let's redo the Jacobian matrix. So we've got the determinant of the Jacobian matrix. All right. So now you can see we can get the inverse, right? And here's the inverse of the Jacobian. Now, this typically, this evaluation starting from here down is in the code is going to be done at a quadrature point, at a particular psi and eta. But for this routine, I left it analytical because Mathematica can handle that, okay? But again, you have to remember, this would typically be at a quadrature point inside some sort of quadrature loop. All right, so we got the Jacobian. We got the inverse. You can see it's a rational function. And now we can get the actual inverse derivative terms, like the derivative of psi with respect to x, the derivative of psi with respect to y. Those are just the elements in the inverse Jacobian matrix. And then you can use the chain rule to get the derivatives. So for example, the derivative of the first shape function with respect to x is going to be the derivative of the shape function with respect to psi. Again, you can hard code that in, that's known. And then the d psi dx, which comes from this term in the inverse Jacobian. And the second term is chain rules with respect to eta. So you've got the d eta with respect to x right there. Okay? And you can go through and it does the same thing for the second shape function, and the third shape function, and the fourth shape function. And so you can put all these into the B matrix, right? So the B matrix has the following form, right? And here you can see you got the derivative of n1 with respect to x, derivative of n1 with respect to y, derivative of n1 with respect to y, derivative of n1 with respect to x. And here it is for the second shape function, n2 with respect to x, n2 with respect to y, n2 with respect to x, n2 with respect to y, third shape function, and the fourth shape function. So that's the B matrix. Again, it's a function of position. All right. The next thing we want to do, well, we're going to get the stiffness matrix. So first I get the plane stress material stiffness matrix. So I define Young's modulus and Poisson's ratio. I use Y for Poisson's ratio because capital E is reserved. And we covered this. Here's the stiffness matrix, the material stiffness matrix. And now we're down to the point where you want to actually integrate B transpose times C times B times the determinant of the Jacobian over the parent element to get the element stiffness matrix. Now, I tried to do this in Mathematica, and on my computer it took like an hour, and then it timed out, and so which is reasonable. I didn't really expect. I don't think it is an issue even of computational time. I believe it's just it cannot evaluate the integral for this rational function. You got to look. You got a rational function here that gets multiplied twice, so this stuff gets squared, and then the Jacobian is also a rational function. So this is a kind of a really nasty rational polynomial type of function that you have to integrate. So it's not really going to work out so well. So instead, we'll do the numerical integration from this point. All right. So here we're going to do a 2 by 2 quadrature rule. So we're going to integrate. These are the two quadrature points, minus 0.57735 and positive 0.57735. And then the respective weights, which are both 1. So the function that we're going to integrate, the integrand, is the transpose of b times c times the b times the determinant of the Jacobian. So this is the f of psi eta, so to speak, for the quadrature rule. And here we go. Now you can evaluate the system matrix, the stiffness matrix, excuse me. So this is the integrand multiplied by the W1 and W1. So this is at the integration point in the lower left corner, okay? And we've put in for psi and eta minus 0.5773. So this is at minus 0.5773 minus 0.5773. That's the first term. The second term, this is the integrand evaluated at the second quadrature point, which is the lower right. So, you know, I probably could show a picture. Probably should have done this before. Let's see how this works. All right, so here's the parent element we're integrating on. I can't tell whether this fits in the window. I think it does. I'll move around a little bit. So the first term is the evaluation at this quadrature point. The second term here, we're evaluating at this quadrature point. This third term is the integrand evaluated at the third quadrature point, which is right here. So that's at, oh wait, did I get this backwards? Oh, I did this in a different way, right? Okay, so here's the first term. The second term is at eta equal, so the second term I did here, okay, because it's psi equals the negative and eta equals the positive. The third term is at this point, and then the fourth term is at this point, okay? I probably should, usually I do it this way. That's usually the way it rolls out in a for loop, but anyway. And so you can evaluate that. Oh, maybe I didn't figure out what the integrand was. And I also didn't. Okay, so there we go. Now this should work. There you go. And you get the number. So numerically, this is the stiffness matrix, okay, for that particular element. You can go through and you can change the element coordinates. For example, you can drop this to, then you can evaluate the notebook, let it run through, and that'll give you the stiffness matrix for that particular element, okay? So that's how it works. So actually, I know we don't do this in this class, but again, for those, some people watch these videos who don't take the class. If you're developing your own finite element code, I mean, I always use Mathematica to check my actual codes, because if you wrote a program to do this in MATLAB or Fortran or C or whatever, you could actually test a particular element in your code and also test it here and make sure that you get the same numbers, right? So, okay. So I hope that was kind of useful. Again, just to go over the steps. First, we define the coordinates. Once we know the coordinates, we also have hard-coded the shape functions, and actually that can be done before if you want. From the shape functions and the coordinates, we can get the mapping, x as a function of psi and eta. From that, we can then get the gradient, or the tangent map, which is the Jacobian matrix. Now, normally, again, at this point, we would actually do this at a particular psi and eta point, right? Because we're using this information just to really determine the value of this integrand down here at a quadrature point, right? So B, this is what we're really trying to get is B, right? So that has to be at the 4 quadrature points. So normally in a code, what's going on here would be at a quadrature point in a loop, okay? We can get the determine the Jacobian. Hopefully it's positive. The inverse. From the inverse, we can get the derivative terms that we need for the chain rule to get the derivatives of the shape functions with respect to x and y. Once we know the derivatives of all the shape functions with respect to x and y, we can form the B matrix. Again, that would be at the quadrature point. Actually, the C matrix is constant for all of them, so you can put that outside everything. I could have done that up front. And then we do the quadrature evaluation and form the stiffness matrix. Okay? All right. Well, that's pretty much it. Like I said, I'll post the spreadsheet on the Blackboard site. Okay?